That was not a dam failure. The dam is still standing. You can drive to it. 860 feet of double-curved concrete arch, 11 feet thick at the crest, holding a valley in northern Italy. It took forces far beyond anything it was designed for on the night of the 9th of October, 1963, and it came through with minimal damage. 2,056 people died anyway. In Longarone, a town of about 1,300 people in the flood path, 1,269 of them were killed, 94%. The dam did its job. The mountain next to it had been failing for 3 years, in measurements the operators took every week. I'm Ray Callahan. 4 years before that night, a young geologist named Edoardo Semenza stood on a rock outcrop above the reservoir and worked out that the entire southern slope of the Vajont Valley was an ancient landslide, a mass of rock that had already failed once in prehistory and was sitting there restacked and waiting. He wrote it up, and the report went to the dam's designers in June of 1960. Edoardo Semenza was the son of Carlo Semenza, the engineer who designed the dam. This episode is about what the company did with that report and about the 3 years of measurements that came after it, because they did not ignore the mountain. They watched it. They instrumented it. They discovered they could speed it up and slow it down with the reservoir level, and they wrote the numbers down every week. On the 4th of October, 1963, 5 days before the valley was destroyed, the mountain was moving 8 inches a day. Every figure in this episode comes from the American Dam Safety Case record, from peer-reviewed geotechnical literature, or from the Italian criminal proceedings that followed. Where the record is thin, I will say so. The Vajont Dam was built to be a record. When it was finished, it was the tallest thin-arch dam in the world. Construction ran from July of 1957 to September of 1960. 860 feet tall, 623 feet across the crest, 16 gates along the top. At the crest, the concrete is 11 feet thick. At the base, 73. That thinness is the point of an arch dam. A gravity dam holds water back by being too heavy to push, which is why gravity dams are enormous wedges of concrete. An arch dam does something cleverer. It curves upstream, so the water load compresses the arch, and the arch carries that compression sideways into the rock walls of the gorge. The canyon becomes part of the structure. That is why an arch dam can be 11 feet thick at the crest and hold back 800 feet of water, and it is why you only build one in a narrow gorge with competent rock on both sides. An arch dam is a structure that borrows its strength from the mountain. Hold that sentence, because it is the irony this whole story runs on. The reservoir was designed to hold 138,000 acre-feet, and filling began in February of 1960, while construction was still finishing. Now the geologist. In 1959, Edoardo Semenza identified an outcrop on the valley's southern flank, a formation called Col Isolato, the isolated hill, and read it as the front edge of an enormous prehistoric rock slide. The mass had come down long before anyone was there to see it, and had come to rest on the slope above what was now a reservoir under construction. What he was reading in that outcrop is a thing geologists learn to see and almost nobody else does. A slope that has failed before does not look like a slope that has not. The rock is disordered where it should be layered, the bedding is rotated, and the debris sits in a shape the valley could not have carved. Col Isolato was the front of that mass, a piece of the old slide left standing when the river cut down through the rest of it. He and a colleague, Giudici, documented it. The report was commissioned by SAID, the company that built and operated the dam, and delivered to the designers in June of 1960. Somebody wrote this down before it happened. I want to be careful about what that report did and did not say, because overstating it would be easy and dishonest. It did not predict a specific collapse on a specific date. It hypothesized that the slope was an old landslide mass, which, if true, meant the rock was already broken along a surface that had failed before, and that filling a reservoir against it was an experiment with a known bad precedent. That was the finding, and it was a finding about the ground rather than about a date. 5 months after it landed on the designers' desks, the slope moved. On the 4th of November, 1960, with the reservoir standing about 600 feet deep, roughly 1 million cubic yards of rock slid into the lake. It produced a wave 7 feet high, and nobody was hurt. Read that event 2 ways, because the company read it one way, and Semenza's report implied the other. The optimistic reading: the slope moved, the dam handled it, the wave was small, the system works. Manageable. The other reading: the hypothesis was just confirmed by the mountain itself. The slope is live, it responds to the reservoir, and the thing that came down was the toe of something much larger. SAID went with the first reading and backed it with scale model testing that produced reassuring results. That detail deserves a moment because scale models of landslide waves are genuinely difficult, and in 1960, the state of the art was not equal to the question being asked of it. A physical model can tell you a great deal about how water behaves, reproducing how a mass of broken rock a mile across enters that water. How fast, in how many pieces, how coherently, is a different problem, and getting it wrong shifts the answer by an order of magnitude rather than a few percent. The model returned a number. The number was comforting. It was also being asked to stand in for the single most uncertain thing in the entire project. Then they started measuring in earnest, and this is where Vajont becomes a different kind of case from almost anything else in this catalog. They installed monitoring. They tracked the creep of the slope, week after week, for 3 years, and they built up a record that shows the relationship plainly. In November of 1962, after heavy rain, the ground was creeping at half an inch a day. Between April and July of 1963, it slowed to about 0.2 of an inch a day. Those two numbers, side by side, are the entire seduction of this case. A slope that speeds up and then slows down looks like a slope under control. It behaves like a system with a governor on it, and every month of data that came back reinforced the impression that the mountain was answering to the operators. What moved it? The lake. When they raised the reservoir, the movement accelerated. When they lowered it, the movement slowed. In one documented case from around 40 millimeters a day down to under 1. They had a dial. They had found it. They understood which way it turned, and they had 3 years of data proving the relationship. So this is a story about people who knew precisely and who concluded from that knowledge that the mountain was something they could manage rather than something they had to leave alone. So why does raising a reservoir move a mountain? The mechanism is not intuitive, and it is the whole case. Start with what was actually under that slope. Post-failure analysis found the failure surface running along layers of clay inside the rock mass. Thin bands of clay interbedded in the limestone. Clay does two things here, and they compound. And the presence of those clay bands is simply what the rock is. The Vajont Gorge is cut through limestone that was laid down in a shallow sea, and thin clay-rich layers between the limestone beds are simply part of how that sequence forms. The material that failed was an ordinary feature of an ordinary geological sequence, which is precisely why it took a geologist to notice that it mattered at all. The first is that it is weak and sheer. A rock slope is held up by friction along whatever surfaces run through it. Put a layer of clay along one of those surfaces, and you have inserted a plane that slides much more easily than rock on rock. That is the lubricant, and in the Vajont case, those planes already existed because the mass had failed along them once before. The second thing is the part almost nobody explains, and it matters more. Clay is nearly impermeable, so when you raise a reservoir against a slope, water pushes into the rock, and where it meets a clay band, it stalls. Pressure builds inside the pore space along that layer instead of draining through. Now the physics. The friction holding a slope up is proportional to the force pressing the two faces of the failure surface together. Water pressure inside the pores pushes those faces apart. It does not lubricate in the everyday sense. It carries part of the weight of the mountain, and every pound of weight carried by water pressure is a pound no longer pressing the surfaces together, which means it is a pound no longer generating friction. Raise the lake, raise the pore pressure, lower the effective friction. The slope does not get heavier. It gets less able to hold itself. And that is the dial they found. It is a real physical relationship. It is measurable, and it is reversible in the direction that felt safe. Lower the lake, the pressure bleeds off. The creep slows down. That last part is what made management look possible. Here is the trap in it. Creep on a slope like that is not a linear dial with a stable setting at every position. A mass sliding on a surface it has failed on before can accelerate in a way that does not come back. And the acceleration is the signal that it has crossed over, because a slope that will stop still decelerates when you unload it, while a slope that will not stop keeps going. By early September of 1963, the movement had reached about 3.5 centimeters a day. In October, it passed 1 2/10 inches a day. On the 4th of October, 5 days out, it was 8 inches a day. At that point, they were lowering the reservoir. It did not stop. On the 9th of October, 1963, the reservoir stood about 782 feet deep, holding roughly 109,000 acre-feet at 2239. 2239 on a Wednesday night, with the towns downstream asleep. The southern flank of Monte Tauk failed. The moving mass was about 1.25 miles wide and 1 mile deep, 350 million cubic yards of rock. That is roughly twice the volume of the water in the reservoir. Picture the arithmetic rather than the drama. You have a lake. Into that lake you drop, in one piece, twice as much rock as the lake contains water. There is no version of that where the water stays. And notice what this does to the question everyone had been asking. For 3 years, the operators had been managing a slope, weighing how fast it was moving against how high the lake stood, treating it as a quantity to be balanced. The moment the mass entered the water, none of that mattered. The reservoir was displaced, wholesale, by a solid object twice its size in under a minute. The slide took less than 45 seconds. That number is worth holding against the 3 years of monitoring that preceded it. 36 months of creep measured in fractions of an inch per day, and then the whole mass crossed the valley floor in under a minute. This is the shape of a shear failure on a surface that has already been used. Slow, 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 and then the friction that was holding it is simply gone, and what is left is a mile of mountain in free acceleration. The water went up the far wall of the gorge and over the top of the dam in a wave that crested more than 330 feet above the crest. About 20,000 acre-feet went over. At the right abutment, there was an office building and a hotel. 40 people died there. Upstream, the villages of Casso and Erdo sat above the reservoir on the opposite side. The wave that went up the far wall of the gorge reached them from below, which is not a direction anyone builds for. In the dam's own control center, 20 technical personnel died. The people whose job was watching the mountain were at their stations, watching it, when it arrived. They had the best information available anywhere on Earth about what that slope was doing, and it bought them nothing. Because by the 9th of October, the only useful decision left had been available 3 years earlier and had already been made the other way. The wave came down the Piave Valley. A mile below the dam, it was around 230 feet deep. It reached Longarone at 2243. 4 minutes. Whatever warning system anyone might have imagined, the useful answer had to arrive before the slide, not after it. And the information that would have justified it had been accumulating in a monitoring file for 3 years. Longarone, Parago, Rivalta, Villanova, and Fay were destroyed. 5 communities, none of which had any relationship to the dam except being downstream of it. In Longarone, 1,269 people died out of roughly 1,328 in the flood path. In Casso and Erdo, upstream, more than 158. And when the water was gone and the sun came up, the dam was still there, with minimal damage, having absorbed forces enormously beyond anything in its design, exactly as its designers had built it to do. The toll was upwards of 2,056. For a sense of what that means in a valley that size, the flood path through Longarone held roughly 1,300 people, and it killed nearly all of them in the few minutes it took the water to pass. The criminal case took years. Proceedings began in the late 1960s, moved to a trial in L'Aquila in 1969, and in 1971 Italy's Court of Cassation identified the 2 men it held principally liable: Alberico Biadani, director of hydraulic construction at SAID, and Francesco Sensidoni, head of the dam service at the Ministry of Public Works and a member of the commission that had signed off on the testing. Sentences were handed down in 1971, 8 years after the valley was destroyed. Most were reduced on appeal. I want to be careful with the word blame here, because a criminal verdict is a legal instrument and not an engineering conclusion, and the two answer different questions. What a court decides about culpability is separate from what the geology did. The reason the trial belongs in this episode at all is narrower. It established, in a public record that can be read, who held which responsibility and what they had in front of them when they held it. I am not going to tell you what those men were thinking in 1962, because I do not know, and the record does not say. What the record does say is narrower and harder. The geological hypothesis existed in writing from June of 1960. The slope confirmed it in November of that year. The instruments then recorded 3 years of movement that responded to the reservoir level, and the reservoir was raised again. The dam safety lesson was written down afterward by Hendren and Patton in language that is almost painful in how simple it is. Any dam site investigation should include a detailed study of the proposed reservoir slopes. If old slides or susceptible areas are found, a detailed stability evaluation under reservoir conditions should be required. That is now standard practice in Italy and in the United States and everywhere that builds large dams. It was not in 1957. Before Vajont, a dam site investigation meant investigating the site of the dam, the foundation, the abutments, the rock that would carry the arch. The reservoir was where the water went. After Vajont, the reservoir became part of the structure under examination. Every slope it would touch, for its entire length, evaluated for stability under the loading the reservoir itself would create, which is the thing worth taking away from Vajont, and it generalizes past dams. Everyone involved was asking whether the structure was safe. That was the wrong question, and it was the wrong question in a way that no amount of care about the structure could fix. The dam was superb. It is still there, empty, 63 years later. The most durable object in the entire story, and the one that mattered least. The failure was in the definition of the system. The reservoir was treated as a thing the dam contained, when the reservoir was in fact a machine acting on every slope it touched, changing the pore pressure inside a mountain that had already failed once. Eduardo Semenza had identified that mountain in 1959 and put it in a report that reached the designers, one of whom was his father, in June of 1960. The mountain was in the file the entire time. It was simply filed under geology in an organization that was solving for concrete. That is the part that travels. Every large project accumulates findings from disciplines that are not the discipline running the project, and those findings arrive as reports that get read by people whose expertise is somewhere else. The Vajont file did not lack the information. It lacked anyone whose job was to be alarmed by it.